That's a good one.
Okay, well, good morning and good afternoon, everybody. Thanks for joining us for the December edition of the CNM Nutrition Seminar Series. This month, we're really excited to bring you the Steele Lab, who's going to talk to you about the quest for the golden calf milk replacer, a tale of metabolomics, gut permeability, and stroopwafels. Mike's lab, if for anybody who doesn't know, focuses on calf nutrition. Mike is a NSERC Industrial Research Chair. And what they're going to talk about today is, I think, largely kind of a history of their collaboration with Trow Nutrition, which will be the focus of today's presentation. And I believe we will hear from Mike, but also four of his graduate students as well too. So if it's okay, Mike, then I will pass the floor over to you and you can introduce your talk and your group to us today.
Yeah, thank you very much, Jen. And it's a great pleasure to be, this is our second time around presenting for the Center for Nutritional Modeling. So this is great. Really enjoy this opportunity. And I really want to share with you some of the results that we've compiled over the last 7 years with Trow Nutrition. And we've been working really closely with them, looking at milk replacer formulations. So we're pretty excited today to share all this information with you. So this story all begins when I graduated from the University of Guelph and I started working for Trow Nutrition. And my background was more in rumen papillae development and rumen epithelial development in transition cows. And I had the opportunity, I was asked by my boss at the time, John Metcalf, do you want to do calf research or cow research? And I said, well, I want to do both. But he said, you have to prioritize. And I prioritized calf research because I was really fascinated by early life nutrition at this point, because this was when my son was born at the same time. So I started this position, was really interested in early life nutrition, started working for a company based with a lot of their research centers in the Netherlands. And this was an exciting time for me. So I loved visiting the Netherlands when I was working for Trow Nutrition. I made a lot of great friends there and did a lot of great collaborations, but I'm just a simple farm boy from Southern Ontario, and I got to gain a little bit of culture and saw the beauty of the Netherlands. I'm just not talking about the countryside and the city, talking about even the arts. But for me, the most beautiful thing in the Netherlands, in my opinion, is the stroopwafel. Okay, I think that this is one of the most best delicacies actually in the Netherlands, which I guess in some circumstances is not saying much, but I really like this combination of syrup and wafers. And I think it's kind of a combination of Canada and the Netherlands. And they're very functional too. And as you can see, they can warm up your coffee as well. And what has happened in our lab due to, all the evolution of different collaborations between Trow Nutrition and the Netherlands is this has become the currency in our lab. So if someone goes to the Netherlands, it's expected to bring back really good stroopwafels. I digress. Sorry about getting off that. Another key aspect of going to the Netherlands is when I was working with Trow Nutrition, some great scientists. So I work very closely with Dr. Lionel Leal and Dr. Javier Martin Tereso. And also at the time, Dr. Harma Behrens too had a pretty big role to play too. But this was what we were doing. It was an exciting time. There was a rebirth of calf research within the company. We actually, with Javier's leadership, developed a new research center that was constructed. So this was a time of great acceleration in calf research. And it was very motivating to work with this team. Now, I decided to go back to academics in 2014 after spending 2.5 years with Trow, but I really wanted to continue this collaboration. And we were really fortunate that they allowed my student to go to the Kempen farm. As you can see here, some images of it just outside of Boxmeer. And actually, my students lived in a haymow on the right, and my first student lived there. And as you can see on the right, there's a Canadian flag there where she was living. But her name was Jaden McPherson, very brave student, never left Alberta, got on a plane to go to the Netherlands and did an amazing experiment looking at plane of nutrition. So we were looking at what does it do to the metabolism when you feed restricted levels of milk, which is still very common, versus more accelerated or more normal levels of milk that the calf would consume. So here's some images of her doing some postprandial tests. She did a lot of glucose tolerance tests. Really proud of this first collaboration with Trow. It ended up evolving into 4 publications from this study. Of course, Jaden's, but also collaboration with John Kent and Priska Stahl, who many of you know, and also Morteza Ghaffari, who's on this call as well, who was my postdoc at the time. So this really got us thinking we can do a lot if we work together. And this came into play, especially when I had the opportunity to move to the University of Guelph. And without Trow Nutrition support, I would have had to stop my NSERC Industrial Research Chair. So they stepped in. I didn't think it was appropriate for Alberta Milk to still fund a person in Ontario through my collaboration, but they stepped up to the plate. And this was a game changer for me when I came to Guelph back in 2018. Instead of shrinking my lab down to 2 students, this allowed me to continue with the same number of students and continue, start with experiments even in the first month of coming to Guelph. So I really thank Trow Nutrition for stepping up and allowing this research to continue. This is the focus of all of our work in our industrial research chair. We are very focused on calf nutrition. Now we study colostrum, we study the effects of the dam, also alternatives to antimicrobials, but where we saw Trow Nutrition playing a huge role is the plate of nutrition aspect. So we did many of these studies like Jaden's where we're looking at high and low planes of nutrition. And it's amazing how much we've published since this time. Here's all of our publications during our collaboration when I've been in academia with Trow Nutrition. So it's really amazing what you can do with a private partner that really appreciates basic research as well, and also the applied. So I think that we're really happy with everything that's going on. And also recently, there's been an alliance formed between Trow Nutrition, also the University of Guelph. So I think that this is just a good indication of a very, fruitful collaboration at all levels at the university. Now, my students currently that are working on these projects are Juanita, who just finished her MSc early this year and will be starting her PhD next year. Annemiek Welberin, who will be defending in early January with their PhD. Juliette Wilms, who's doing her PhD. However, she's a full-time employee at Trow Nutrition in the Netherlands. And also Siobhan Mellers, who will be actually defending her MSc next week on Tuesday. So we kind of made a shift in our research from plain of milk nutrition. Now we know the benefits of feeding more milk, in our opinion. Now we want to look at the composition of milk replacers. So in order for us to really understand this concept, I think it's important for my students to do a lot of the talking because they're the ones doing a lot of the work. So I'm going to first start with Juanita to give us a little bit more background between some of the differences between milk replacer and whole milk and how some of this research evolves. So Juanita, the floor is yours.
All right. Thank you very much, Mike, for the introduction, but can everybody hear me okay?
Yes.
Yes, perfect. As Mike said, I will begin with a short introduction, just talking about nutrient composition and differences between milk replacer formulations as well as whole milk, and then we'll move on into some experiments that we've done in the lab. So caffeine natures are able to get about 50% of their total dietary energy from fat, from the whole milk from the dam, as well as essential fatty acids. But when we look at the way the industry is nowadays, and if we take United States inside, about 50% of the calves there are being fed milk replacer or a combination of milk replacer with whole milk. But when we look at these two diets being milk replacer as well as whole milk, there is substantial variation between the two, especially when it comes to fat and lactose levels. And then we can see that in most commercial milk replacers, we have high levels of lactose and low levels of fat. We'd end up with a diet that provides lower energy density to the calf. And also when we look at the fat, it is quite different when compared with whole milk. And these differences are a result or a consequence of historical availability of milk byproducts, as well as the traditional target for lean growth in the young stock. So the question is why there is so much lactose? So if we get whole milk, it gets processed in order to provide or to produce products that the humans will consume, such as butter and cheese. So these two industries will take the butter fat as well as some of the protein to produce delicious butter and amazing cheese like we have in the Netherlands. And then we're left over with two byproducts such as skim milk as well as whey. And these two byproducts are what we use in the industry to produce some of the milk replacer. But when we look at the lactose content, they're quite high. And that's why we see that these milk replacers are high in lactose. It's also important to highlight that we don't use butterfat in the production of milk replacer. One, because it is quite pricey, and second, because we have alternative options to provide fat to the calves, such as oils coming from coconut or palm oil, as well as tallow in some countries. But when we look at some of the commercial milk replacers, we have some concerns and why there is so much lactose as well as an undersupply of fat. So we know that a calf can more or less handle 10 grams of lactose per kilogram of body weight, which is equal to about 7 liters of a commercial milk replacer for a 45 kilogram calf. However, if we provide more lactose than the animal can handle, we can trigger things as reduced insulin sensitivity, as we've seen in veal calves. And we can also increase the osmolality of the milk replacer, so the solutions that we're providing the calves. And this might target or will reduce water absorption and might increase gut permeability and leading to digestive disorders such as increased diarrhea incidence. Also, the undersupply of fat is a little bit of a concern since fat is crucial for energy supply to the young animal. And some studies in rodents have shown that it might promote gut growth. And in some surveys from the United States, we've seen a linked with lower fat supply and increased mortality.
I was like, better have you.
Your eyes read better.
That's amazing.
Okay, sorry. So in an attempt to formulate milk replacers that have a formulation closer to that of whole milk, several studies have been done in the area where carbohydrates have been replaced by fat, but several studies that are published are there and that are the basics for this knowledge have discouraged the high fat inclusion in milk replacers due to the possible fat deposition in these animals and how it can interfere with mammary gland development in future lactations. However, and to our knowledge, there is no evidence that pre-weaning fat deposition can have an effect in mammary gland development. Also, we know that fat stores can be mobilized during incidents of disease or infections, and there is an association between the nutritional status of a calf and mortality rates. So we should really question the potential risk on targeting only lean growth in the young stock. So with that, I will discuss today. That was part of my master's. And what we did here is that we did a partial exchange of lactose with fat, and we evaluate the effects on milk replacer intake, solid feed intake, as well as calf performance. And the research question for this study is how does micronutrient content of the milk replacer can influence the voluntary feed intake in the calf, as well as its performance. We then hypothesized that when we replace lactose by fat as a source of energy in the milk replacer that we feed in ad libitum, we will see a decrease in milk replacer intake, but we wouldn't see an effect on calf performance. And we were aiming to evaluate those responses, the responses of exchanging lactose with fat, and when we feed it ad libitum on voluntary feed intake growth, as well as feeding behavior. And to evaluate this, we enrolled about 32 calves, and we performed this study in Boxmeer in the Netherlands. And the 32 calves were divided into two diets. The one diet was a high lactose milk replacer that was comparable to a commercial milk replacer. So it contained about 46% lactose and 18% fat. And the other half of the calves were allocated into a high fat milk replacer, which formulation was similar to that of whole milk with about 40% lactose and 25% fat. So for some of the results, we recorded the intakes on the daily basis for the whole study, so for 12 weeks. And we saw that for milk replacer, the calves that were being fed the high lactose milk replacer had higher intake during the pre-weaning period when compared to the high fat calves. But when we put a restriction during the weaning period, we didn't see a difference between the two. And in a similar way, we didn't see a difference in started intake between the two treatments. When we evaluated the protein intake, we did see some differences during the pre-weaning period, and this was attributed to the graded intake of milk replacers seen in the high lactose treatment. However, when we looked at the metabolizable energy intake, we didn't see a difference between the two treatments, despite the non-isocaloric natures of the diet. And this suggests to us that the cows were consuming enough milk replacer just to meet certain energy requirements. Interesting, when we look at the feeding behavior, which was something that haven't been done much in trout nutrition, we saw that about 41% of the high lactose calf had about 41% more unrewarded visits to the milk station. And these unrewarded visits have been widely reported in the literature as behavioral signs of hunger. So one can really question if we were improving the welfare of these animals by increasing the fat content on the milk replacer during the weaning period. We also evaluated growth performance, and we didn't see a difference in body weight between the two treatments. Similar way, we didn't see an overall effect on ADG, or average daily gain. However, we did see that the high lactose calves had certain time points where they were growing a little bit better than the high fat calves, but overall there was no effect in the treatment. For blood metabolites, I just summarized a few here. I put these three as an example, but overall we didn't see much differences. However, in cholesterol, we did see that the high fat calves had greater blood cholesterol when compared with the high lactose. And this has been widely reported in other animals and even in monogastrics, that when you increase the fat content in the diet, you'll see this shift in the blood towards a higher cholesterol level. So just to summarize the main findings of this study, so the isonitrogenous exchange of lactose with fat in a milk replacer that was fed ad libitum did decrease the voluntary milk intake. However, we didn't see an evident effect on solid feed intake or in calf performance. We also concluded that the calves during the pre-weaning period seem to regulate the milk replacer intake based on the caloric density of the diet in order to meet certain energy requirements. And we also saw a decrease in hunger-related behaviors during the weaning period when higher fat is offered to the calves through the milk replacer.
That's great work, Juanita. I really appreciate that. And I think it really goes to show that we shouldn't be too concerned about these high fat milk replacers. In fact, they probably could have a benefit. The animals seem to be doing really, really well. Not many people know this, but Juanita is actually in Europe right now. She's not going to be spending Christmas with our lab. So I just wanted to take this opportunity to give her a Christmas gift. Juanita, thanks so much for everything you do.
Thank you, Mike.
Enjoy.
Stroop waffles.
Yeah, our currency. Yeah, that's great. Again, let's not digress. Let's get back into the material here. So we know that these formulations, they can perform well, but what is happening to the metabolism and the gut function of these animals? And this has really been the focus of my PhD student, Annemiek Welbren, who'll be defending in December. She's currently dialing in from Alberta, where she lives. So Annemiek, do you want to go through the research experiments that you just published in the Journal of Dairy Science this year?
Yeah, of course, Mike. Thank you. So the research question for this study was, how does macronutrient content of milk replacer influence glucose insulin kinetics and gastrointestinal health in neonatal calves? And the hypothesis for this study was the excess of glucose from a high lactose milk replacer would decrease insulin sensitivity and increase gut permeability, and that dietary fat would promote gut development via nutrient receptors. And the objective of this study was to evaluate effects of partially replacing lactose with fat on glucose metabolism, gut histomorphology, and permeability in neonatal calves. And we enrolled 34 calves in this study, and we fed them the same milk replacers as in Juanita's study. So they were fed either a high lactose milk replacer with 46% lactose and 18% fat, or a high fat milk replacer with 40% lactose and 25% fat. And the calves were fed this milk replacer during the first week of life, in which we conducted a glucose tolerance test, a postprandial sampling, a gut permeability test, and a dissection. So during this first week, or the first week of life, the 7 days that we fed these milk replacers, the high-fat group gained more weight than the high-lactose group. And they were fed the same amount of dry matter, but their energy intake was higher due to a greater energy content of the high-fat milk replacer. And even when we calculated the gain per unit of ME intake, these calves still gained more. And it's likely that these calves had more energy available to be retained after their energy requirements for maintenance were met. So we estimated abomasal emptying using a marker called acetaminophen. So we add this to the milk replacer, and you see the radiograph in the right corner shows an abomasum that's filled with milk. And once the milk starts flowing into the small intestine, the acetaminophen is readily absorbed. So from concentrations of acetaminophen in blood, we can calculate abomasal emptying rates. And so the graph shows that the concentration of acetaminophen was lower in the high-fat group, and the abomasal emptying rate constants were also lower in this group. So in other words, feeding a high-fat milk replacer slowed down abomasal emptying, and this may be due to a release of cholecystokinin, or CCK, in response to dietary fat. And this delay in abomasal emptying may be beneficial with regards to nutrient digestibility, but we did not measure that in this study. So it means that for the high lactose group, greater quantities of a high lactose milk replacer entered the small intestine, which was reflected in higher concentrations during postprandial sampling, as well as higher concentrations of insulin in the high lactose group. So these graphs show the glucose and insulin concentrations during the glucose tolerance test. So we see that the calves were infused with glucose, as indicated by the blue arrow and the peak in the glucose curve on the left. And 20 minutes later, they were infused with insulin, as indicated by the orange arrow and the peak on the right. So from the clearance of glucose per unit of insulin, as indicated by that yellow arrow, we can calculate insulin sensitivity. And this was not different between the two treatment groups, and that is in agreement with other studies comparing high lactose and high fat milk replacers. So individual weights of organs did not differ between treatment groups, but the total small intestine and total gastrointestinal tract was heavier in the high fat group than the high lactose group. So this was not due to a difference in length. So potentially dietary fat may have promoted mucosal hyperplasia via luminal factors, but we only found minor differences in histomorphology and nutrient sensing receptor expression. So at this point, it is unclear what caused this difference in gut weight. And we knew that intestinal permeability is impacted by osmolality. So we just wanted to understand how the osmolality of digesta changes as it transits through the gastrointestinal tract. And so this graph shows the data from all the calves because there were no difference between treatment groups. And we saw that as the digesta flows from abomasum into the duodenum, the osmolality increases, which we interpret as a consequence of digestion of nutrients because that increases the number of solutes. And then as the digesta moves further down the GI tract, the osmolality decreases, which could be a consequence of absorption of these solutes. So then moving on with intestinal permeability, there was no difference in lactose or in demannitol recovery in urine, but lactulose concentrations in plasma were higher in the high fat group than in the high lactose group, with no differences in demannitol. And this was a little unexpected because we didn't think that by bringing the composition of milk replacer closer to that of whole milk by increasing the fat content, we would induce a leaky gut. So on the one hand, we started questioning the methodology. For this study, we added the markers to the milk replacers. So is there potentially any interaction with one of the macronutrients of milk replacer that caused this difference? And Siobhan will go into this a little bit more later. And on the other hand, lactulose is considered a marker for paracellular permeability. So it is possible that the calves of the high fat group suffered from more mucosal damage or damage to their tight junction proteins. And so when we evaluated gene expression in proximal jejunum and ileum tissue, we saw that the expression of tight junction proteins claudin 2 and tight junction protein 1 tended to be lower in the high fat group, which is in line with the increased permeability in this group. And then interestingly, we also saw that pro-inflammatory cytokine interleukin 1b expression tended to be higher. And so that made us wonder if the fat sources that we use for these milk replacers, which are coconut and palm oil, may have something to do with this finding. And this too, Siobhan will go into more detail about this. So the main findings of this study was that the high-fat milk replacer slowed down abomasal emptying. It decreased postprandial glucose and insulin concentrations, but did not affect insulin sensitivity. The high-fat milk replacer increased gut weight, which may be beneficial for intestinal development of neonatal calves. And the high-fat milk replacer increased gut permeability, which made us question the methodology as well as the suitability of the fat sources used.
Yeah, that's excellent, Annemiek. I think you're one of the first people who really sunk their teeth into some of the mechanisms of metabolism and gut function with this comparison. And a lot of you know Annemiek is in Alberta right now, so she's not going to be attending our Christmas party. So I just wanted to give you this gift, Annemiek, just to make sure that you feel still a part of the team.
Oh, thank you.
Yeah, no problem. My pleasure. Yeah, and exactly. It was you who got me onto them, so thank you very much. Now, let's not digress more. Let's go back to the task at hand, everyone. And we've done the high fat, high lactose comparisons, but what about protein? And should we be looking at, what we were looking at with Annemiek, or should we be making these comparisons? And how does this milk replacer compare to something that's similar to a whole milk? And this is where Juliette Wilms, who's currently a research scientist at Trow Nutrition, but is also doing a part-time PhD here at the University of Guelph in this area. So Juliette, would you like to share some of your newest research?
Yes, thank you, Mike. So indeed, we looked a lot into the partial replacement of lactose by fat in milk replacer in order to get closer to whole milk. But we never generated data of cows fed whole milk, so we never know if the difference we see are actually relevant and what should be the normal values. And we also wanted to look into high protein formulations, which are not that common on the market, but can still be fine. So the research question was, how does macronutrient profile in milk replacer influence growth and metabolic responses? And we hypothesized that high fat intakes, either from whole milk or from high fat milk replacers, would result in a slower growth, distinct metabolic profiles and postprandial responses compared to milk replacer with high lactose or high protein. And we evaluated how the macronutrient profile of milk replacer or whole milk would affect growth performance and metabolism. And we performed 2 experiments in which we had whole milk powder with 26% fat, a high fat milk replacer with 25% fat, a high lactose milk replacer with 44% lactose, and a high protein milk replacer with 26% protein. In the first experiment, cows were group housed in the department that you can see on this photo. From week 2 to 7, they were fed ad libitum. From week 7 to 10, we gradually weaned them. And in weeks 11 and 12, they were fed solids only. And we saw that performance was enhanced in cows fed the high lactose milk replacer compared to cows fed whole milk. And there were no differences between high protein and high fat. Now, if we look at the intakes, it was quite interesting, especially during the pre-weaning phase, because intakes were enhanced in cows fed the high lactose and the high protein milk replacers compared to the whole milk. And it was also higher in high lactose than high fat. And here I should mention that we fixed the concentrations of those 4 treatments to 135 grams per liter. So the energy density of the milk was not the same. It was lower in the high lactose and the high protein milk replacers. And as Juanita mentioned, we can conclude from this that calves may drink to reach a certain energy requirement. At least they drink milk replacer based on energy density. Because we see here in the pre-weaning phase that there were no differences in total metabolizable energy intakes. Every week we measured some blood parameters, and Morteza actually did this heat map where we can see the So a blue color represents lower concentrations relative to other groups and other treatment groups, and the red color represents higher concentrations compared to other groups. And we see here, for example, that calves-fed whole milk powder had lower blood acid-base parameters in the blood. And this was actually because this whole milk powder was overheated during the drying process and the protein fraction was damaged, and it led to higher diarrhea in week 1, 2, and 3. So we saw an increased metabolic acidosis severity in that group. But then we also see other differences in IGF-1, serum amyloid A, urea albumin. So although the growth performances between the 3 Milk-Placer treatments did not differ much, we see large differences in the metabolic profile, and it's important to understand what are the consequences for the future health of those animals. I took here 2 examples that I think are very relevant. The first one is the insulin-like growth factor 1, IGF-1, which was enhanced in cows fed high lactose and high protein milk replacers compared to the whole milk powder. And there was also a trend between high protein and high fat. And this is actually this is probably due to the increased concentrations of insulin-releasing amino acids in the high protein and high lactose groups. Because although the protein were lower in the milk replacer of the cows getting the high lactose milk replacer, because they had high milk intakes, their protein intakes was also quite high. And this was actually described in infant nutrition, where infant formula with high protein leads to increased level of IGF-1 in the blood. And this was associated with greater growth in infancy, but an increased risk of cardiovascular disease in later life. So this is maybe not what we want for replacement heifers. Then we also looked into serum amyloid A, which is a marker of inflammation, and it was greater in cows fed the high-fat milk replacer compared to high lactose and whole milk. So this could be linked to the fat intakes, but also to the fat composition, because the intakes of fat were the same between the whole milk and the high-fat treatments. And one of our explanation could be the ratio between omega-6 to omega-3 fatty acids, which is really high in the milk replacer fat, which is a blend of coconut and palm oil, and it's about 40, while in whole milk it's usually around 5. And this was shown to lead to inflammation, but the high-fat fat calves were in good health in this experiment, so we have to see if these differences are relevant and how we can improve this. Then we performed another experiments using the same 4 treatments, and we looked into the first 4 weeks of life. Calves were individually housed. They were fed 3 liters 3 times daily, and in week 4 we did a postprandial sampling, and we looked at abomasal emptying using the same technique that Annemiek just described. So in this experiment, we didn't see differences between high fat and high lactose. The gastric emptying was the same. But that's maybe linked with the feeding scheme or with the age of the animal. That was different from the study of Annemiek. And what was interesting here, it was that gastric emptying was slower in cows fed high protein or the whole milk powder. And this is probably linked with the higher protein intake in the high protein group and to the protein composition in the whole milk group. Because the protein fraction of the whole milk contained 90% of casein, leading to a formation of the curd, and that's probably why we see a slower gastric emptying. So because we have curd formation to a larger extent in the whole milk fed group, so probably there is the curd formation, and the liquid fraction of the milk is rapidly flowing to the intestines, and this fraction contains the lactose, and that's probably why we see a greater peak of glucose and insulin in cows fed whole milk. And we also found that the area under the curve for glucose was greater in cows fed whole milk and high fat. And when we look at insulin, the area under the curve was greater for cows fed the high protein milk replacer compared to whole milk and high fat. And again, that's probably linked with the increased concentration of insulin-releasing amino acids because of the higher protein intake in that group. And that's very consistent with the IGF-1 data I just presented. Thanks to Bonn University, we also measured adiponectin and leptin into those samples. And we saw that adiponectin concentrations were consistently more elevated in cows fed high lactose compared to all 3 other groups. So adiponectin allows to lower blood glucose by inhibiting the expression of hepatic gluconeogenic enzymes and the rate of endogenous glucose production. And then we also found that there were lower basal concentrations of leptin. And research has shown that high adiponectin and low leptin concentrations can stimulate feed intakes in rodents. And this may explain why in ad libitum system, we see that cows drink so much of the high lactose milk replacer. So it may not just be linked with energy density, but also with a certain hormonal signal that we send to those animals. And some literature also hypothesized that a high ratio between adiponectin to leptin may be predictive of reduced insulin sensitivity. We also measured the postprandial triglyceride dynamics, and we saw that it was more elevated in the whole milk and the high-fat groups, which makes sense because high-fat intakes was higher. But what was interesting is that the intakes of fat in the whole milk and the high-fat were the same, but the postprandial triglyceride dynamics were not, and that can be linked to the composition of the fat, which is widely different between these two treatments, and we have to understand what should be the optimum and how we can work on the fat composition. And this also shows that maybe the cows fed whole milk in ad libitum setting, they drink less milk because they have a higher triglyceride, higher postprandial triglyceride concentrations. They have a greater glucose peak and they have a slower gastric emptying. So maybe this is why they drink less, because they have a better feeling of satiety and they get a different signaling. So the main findings of these two experiments were that the intakes of milk replacer in ad libitum system are probably driven by the energy density of the milk, but also by the postprandial dynamics and the hormone signaling. And we saw a profound metabolic effect of the high lactose and the high protein milk replacers on the hormones, insulin, IGF-1, leptin, and adiponectin.
That's awesome, Juliette. I really appreciate you doing this research and opening up our mind to this comparison of whole milk versus milk replacer at similar macronutrient composition and adding that protein part of the story. As everyone knows, Juliette lives in the Netherlands, so she won't be joining us for Christmas. So I want to take this opportunity to say thanks for all your hard work, Juliette. I really appreciate it.
Thank you, Mike.
Yeah, no problem. So,
buffers.
Yeah, exactly. You guessed it. So this comparison is so fascinating between the similar macronutrient compositions of whole milk versus milk replacer. And we saw some of these differences even at the gut level, and we wanted to take a deeper look at this. And this is where Siobhan came in. So Siobhan is going to be defending actually next week. So she's going to be talking about just a little bit of what she's going to be defending on Tuesday of next week. So Siobhan, would you like to take it away?
Yes, thank you, Mike, for that introduction. I'm just going to give everyone a small snippet of what I'll be defending next week. So this was actually a subset of one of the studies that Juliette described. So our research question was, how does feeding a milk replacer with a similar macronutrient profile to whole milk influence gastrointestinal tract development? We hypothesized that the composition of the fat from whole milk powder would promote gastrointestinal tract growth and development, as well as altering the composition of the gastrointestinal tract and decreasing permeability. Our objective was to compare a high-fat milk replacer to whole milk powder, both having similar macronutrient inclusion in terms of fat, protein, and lactose, on gastrointestinal tract structure, function, and composition in pre-weaned calves. You can see below that we used the same treatments as Juliette previously described. We used a whole milk powder with 38% lactose, 26% fat, and a milk replacer with very similar macronutrient composition at 38% lactose and 26% fat. These calves were fed 3 liters 3 times daily, and we raised them to 4 weeks of age, and at 3 weeks, we assessed gastrointestinal tract permeability, and at 4 weeks of age, these calves were dissected. As Juliette mentioned, the fatty acid profile of whole milk and milk replacer is very different. Here we have the fatty acid profiles of the 2 treatments in my experiment. The milk replacer is a 65% palm and 35% coconut. And as we can see by the yellow line, there are numerous fatty acids in the milk replacer that are at very low levels or missing, as that line is at 0.1% of fat. For example, C4 butyric acid is only present in milk replacer at approximately 0.0% fat, and it has to be intentionally added to many milk replacers, whereas in the whole milk powder, it's present at over 3% of fat. As well, you can see those differences in the omega fatty acids that Juliet mentioned as well. So we assessed gastrointestinal tract permeability at 3 weeks of age, and we found increased paracellular permeability in the whole milk powder calves in both the chromium EDTA at 0 to 6 hours, as well as 0 to 24 hours, and in the 0 to 6 of the lactulose. Paracellular permeability refers to permeability between cells, which is usually discussed with the functioning of tight junction proteins. We did gene expression on some tight junction proteins and found no differences in this experiment, which is contrary to previous literature. However, it's important to note that the whole milk powder had a lower whey protein nitrogen index at approximately 1.8 milligrams per gram compared with 6.7 milligrams per gram in the high-fat milk replacer. And this is due to overheating during the drying process, and that actually lowered the dry matter digestibility of the whole milk powder treatment and may be responsible for some of the differences we see in gastrointestinal tract permeability in this experiment. In the gastrointestinal tract gross morphology, we found increased gut weight in both the foregut and the hindgut of the whole milk powder fed calves. Specifically, we see an increase in jejunal weight in the small intestine, and this may lead to greater potential for nutrient absorption. So then we wanted to find out potentially what was responsible for the difference in the weights between the two groups. So we did some histology. And in these results, we found an increased surface area index in the distal jejunum of the whole milk powder fed calves. We calculated this by generating H&E stained slides that you can see in the photo on the right and measuring villus height, width, as well as crypt depth and width, and used an equation to generate this relative surface area index of each of these small intestinal tissues that you can see. We also found a difference in villus width in the distal jejunum of the whole milk powder fed calves. We also measured muscularis thickness and found no difference. We also looked into immunohistochemistry at the Chi67 antigen and also found no differences. Lastly, we looked at phospholipid composition of jejunal tissue, as there are many studies suggesting that the diet affects composition of jejunum tissue or gut tissue in general, and that changes in the composition can actually affect gut permeability. There are numerous in vitro and some ex vivo studies showing that specific polyunsaturated fatty acids can alter permeability and specifically alter and affect tight junction function and gene expression, although we didn't see that in this experiment. We also generated Pearson correlation coefficients and found that the phospholipid composition in this experiment was correlated to both transcellular and paracellular permeability results. Additionally, it's important to know moving forward, the tissue composition affects many aspects of physiology, including membrane fluidity and transcellular permeability. Saturated fatty acids are a large component of determining membrane fluidity, as you can see in the diagram. More saturated fatty acids will lower membrane fluidity. However, cholesterol also has a large impact in determining membrane fluidity, although it's not well quantified the cholesterol levels between whole milk and milk replacers. Cholesterol can affect membrane fluidity because it interacts with sphingomyelin, and integral membrane proteins are located between sphingomyelin and cholesterol. So this could be affecting some of the functioning of the enterocytes in the gastrointestinal tract tissue. So our main findings from this study were that the foregut and lower gut mass are increased by whole milk powder feeding, and this could be due to the differences in fatty acid profile. As well, calves fed the whole milk powder have greater paracellular permeability, although we have to keep in mind the difference in the dry matter digestibility in this case. And lastly, intestinal tissue composition is altered by the diet and correlated to gastrointestinal permeability measurements.
Thanks, Siobhan. That was an awesome summary of what some of the things that you're going to be presenting next week.
Thank you, Mike.
And I know that we're going to see each other because you're in Guelph, but I just want to be fair and make sure that you feel rewarded. So here you go.
Oh, thanks, Mike.
No problem. Oh, got it. Yeah, who would
A half a bag of Stroop waffles.
I can't help myself, Joanne. I'm really sorry about that. I just couldn't help myself. So sorry about that. Now let's focus on what we've talked about, what we've been doing over the last 7 years, but where we're going in the future. And I think that this is a really sound and productive collaboration. And I'm really happy and proud of all the success we've had over the last 7 years. Where we're heading, and this is where Juliet's PhD will be focused on, is really fats and fatty acid composition. Also, continuing to investigate a lot of the metabolic programming experiments that we conducted through the years. And now we're focusing especially on a 5-year NSERC Alliance grant looking at dairy beef. We're really excited by this because we think dairy beef is a really interesting model for what we study in metabolic programming. And we think that this area in the industry is also growing. So, to continue on with the NSERC IRC and all the success we had, and the IRC actually ends in April 2022, we like to continue it on for 5 years and really focus on this area. So I see this as a long-term project for our lab, and we'll be investigating and trying to find the optimal milk replacer for farms, since 50% of calves are fed milk replacer here in some provinces as well as the world. So we think that this is very important. So we hope that you've enjoyed this story that we laid out today. I really want to thank especially Trow Nutrition for making this collaboration so wonderful for my students. Unfortunate that a lot of these students couldn't go to the Netherlands over lockdown. However, I'm hopeful that someday we can start exchanging more students again like we used to. But thank you very much. Also wanted to thank all of our collaborators for this research. University of Bonn was mentioned as well. They played a big part as well in Helga Sauerwein's lab, and all of the other academic and industry collaborators that had played a little part in all of this research. So I'd be very happy, and we're all very happy to accept questions, everyone. So if there's any questions, please don't be shy. Not all at once, though, if that's okay.
Yeah, you guys can feel free to speak up, or you can type a question in the comment section, or just feel free to unmute yourselves.
I'll lead the charge if you don't mind.
Someone mute this man, please. The security of this meeting is not very good, Jen.
It was really fun listening to all the presentations, and I learned a bit. So thank you for brightening my Thursday here in Saskatchewan. I have a general question. I posted a message in the chat, but I think this goes across all studies, particularly those where you're measuring permeability. And we often think about permeability as being negative, but as was just mentioned, permeability really accounts for both transcellular and paracellular passage. And these markers that we use are not perfect in exclusively identifying a single mode of translocation. So I just wonder, maybe we shouldn't be thinking about greater permeability as being negative, or can you provide proof that the greater permeability actually leads to negative systemic responses, such as pro-inflammatory responses that could be perceived as negative?
That's a great question that we've been talking about for over close to 10 years, Greg. But I'm going to let my students who have also thought a lot about it just comment a little. I'm wondering if Annemiek or Juliet want to comment, seeing as they were the first people who started to look at gut permeability in our lab. What do you think of this whole notion that we just think, all of a sudden an increase in gut permeability, we automatically think it's negative? What's your opinion what is the scale of these metrics of gut permeability and what other things we should be looking at. Juliet, do you want to start or Annemiek?
I will let Annemiek start. And
I was gonna say the same. Yeah, you're right. Like in general, we think there is a negative connotation, but as far as we know, there is no real proof related to that, like related to health parameters or like even like LPS concentration in blood or infection. I think my study was the first where we also looked at tissue and where we noticed that tendency for increasing expression of interleukin-1b. Because before that, we were really just only thinking that it was the interaction with the diet, with for example, fat in milk replacer. So that question is still unanswered. I think my last study also, for my last study, I looked at the omega-6 to omega-3 fatty acid ratio. So I compared a milk replacer with a ratio of 40 to 1 with 6.5 to 1. And I think there, because we administered the markers and 3 hours later we fed the calves. This was just due to like practical like scheduling of the day. And we do seem to pick up some effect like directly after the meal, where the marker recovery or the concentrations in the blood seem to diverge between the two groups. So that is kind of an indication that the diet or like feeding does directly impact intestinal permeability. So I think we're just like trying to figure out the impact of the diet and yeah, the correlation with health parameters is still open.
And Juliet, can you comment a little bit too and talk about some of your diarrhea studies looking at gut permeability or inducing more severe gut permeability and how it compares to these studies?
so actually in diarrhea calves, because we didn't have the diarrhea etiology, we couldn't conclude anything regarding gut permeability, although it was really high in some calves. But in the study of Siobhan, we know that the milk replacer was suboptimal because the protein fraction was damaged. And in the ad libitum study, those calves really suffered, and they had 30% of them were treated for diarrhea, which was much higher than in other groups. So in this particular case, the higher permeability at least made sense with health parameters. I think what we lack and what we measure, but we still don't have the results, is the permeability for calves fed fresh whole milk. And I think in 2022, we'll have those data.
Yeah, and measuring gut permeability in calves is somewhat of a new thing. In fact, Greg, with your collaboration with Katie was a postdoc, was one of the first examples of it. So I think what we need to do is just continually measure it and then start comparing it to all these other metrics to see, is it really that bad if gut permeability increases by 10, 20%? Maybe it is, but I don't think that we're in a place to do that because we haven't measured it enough. We're still working out how to dose actually the markers and actually how to properly quantify some of these markers.
Yeah, I look at it another way, and there are a lot of nutrients that we might want to promote absorption, and these would be transcellular absorptive pathways that might be enhanced by a more fluid membrane. Short chain fatty acids would be a good example. And so maybe not so relevant for young calves and intestinal absorption, at least until you get to the hindgut and there is some fermentation going on. But let's not forget that permeability could actually be positive in some cases and might actually drive more metabolizable energy supply simply by modulating gut function. Great comments and stimulating answers, though.
Yeah, and your work, Greg, really inspired to look at tissue composition from our joint lab meeting in the past. So thank you for that. Is there any other questions?
May I, Mike?
Yes, and thanks so much for everyone from Trowel coming here. I really appreciate it. And a lot of people were involved in this research, not just Javier and Lionel. I remember some of the first work we did was with Stefan Rauers too, and I'm happy to see him here too. So I wanted to thank him as well. But before you ask your question, Javier, so shoot.
Well, if there is something remarkable about this collaboration is that I think for the first time, milk replacer composition has been looked into greater insight than pure growth performance or feed conversion. And there are so many new parameters that we have been together measuring. And we struggle to interpret what's positive, what's not so positive, what's better, what's worse. My question, especially to your students, Mike, is for all these things that we've been measuring from our nasal emptying, the permeability, dissection parameters, what do you think is the desired phenotype that we should be aiming for with a milk replacer composition? And an additional question would be, is there a difference between that desired phenotype in the calf when we are talking about a replacement heifer or when we're talking about a male calf that will go into grower and feedlot phase?
Can I just say one thing? I think that some of the phenotypes we look at in calf nutrition and management are a little bit flawed. I think although average daily gain is something that you should be looking at, I think the functionality of the animal and maybe linking that to long-term productivity and lifetime productivity is really the phenotype we need to start gathering more. So more of the functionality of the calf, which we've been trying to do. As for the male calf, I think it's completely different because what you end up with will be slaughtered at 18 months. So the target performance is totally different. And that's, I think, a large part of what we've been trying to do is expand this phenotype rather than just average daily gain pre-weaning to look at everything and in particular lifetime production, I think is where we really need to focus on. And that's what's so intriguing with the dairy beef. It's actually feasible to do that a little bit more with 18-month lifespans. But I'm curious to know if my students have any comments on this great question that Javier is.
Yeah, I was going to say the question was to your students.
Oh, sorry. So students, am I wrong or am I right? I'm not sure. I want to know, or can you expand?
Yeah, no, I agree with what you said, Mike. And I think what I would add is actually what Juliette already mentioned is if we have a comparison with calves fed whole milk, we have a better understanding what it should look like and how the performance compares of the calves that we're currently feeding.
And also, if we look at the data that we have, the metabolic data, and if we compare that to infant nutrition, we see that what we find is really consistent with what they have done, and it shows that the milk replacer should be formulated as close as possible to the biological reference.
Yeah, I agree with what Mike said and what has been said by the other students. And I think we need to move away from thinking of about the calf as a calf and start thinking as the future milk producer or the future steak that you're going to have in your plate, more or less, and see how we're going to achieve that top quality and ensure that they have a decent and good welfare through the whole life, and instead just being focused on just providing the milk for the calf.
I guess I'll just add a little bit here. I agree with all my peers. I think it's really important to do some more studies in looking at maybe how these different metabolic and gastrointestinal measurements will carry them through events like weaning and see if it improves their performance, improves their welfare. I think studies like Juanita's are really important, showing the difference in the unrewarded visits and potentially hunger. I think we should be also focusing on what gives the calves a good life for as long as they will be alive, whether that's for the steak or for milk production.
Great, thank you. Couldn't have done better myself. Any other questions, folks? Morteza has a question, who's
Yes.
contributing to this research from the University of Bonn. So actually, Morteza was involved at the beginning of it when we started to do this work, when he was a postdoc for me at University of Alberta. And now he's working in Helga Sauerwein's lab at the University of Bonn. So great to have you here. Look forward to your question.
Thanks, Mike, for the introduction and for the amazing presentation today. I'm really impressed. But I have one question that I don't know if you have your answer with your study now, but maybe in the future. But from the milk replacer composition, we see some differences. But do you expect any long-lasting effects from this milk replacer composition on calf performance, maybe after weaning? And if so, what tissue do you expect to be more affected from these diets?
No, so are you just talking about the post-weaning phase, Morteza, or lifetime?
Lifetime and post-weaning, maybe.
Yeah, I would be focusing especially on the high lactose, high fat, on insulin sensitivity through life. So I'm not sure if it's a specific tissue that I'd be looking at, if possible. I'm not sure if it's possible with slaughter-based, but I'd love to look at the pancreas more in some of those experimental models. Unfortunately, it's really difficult to get, but you can measure the responsiveness of it. So I would be doing a lot more in vivo tolerance tests, I think, to really follow these animals for their entire life. But until we do that, we can't really say that much about this topic. And I think that's for everything in CAP research. If we don't follow them, it's kind of impossible. The issue that we have is that there's not a lot of funding agencies that will give you 10 years of funding to do so. And I wanted to mention that it's actually Dr. Lionel Leals was one of the first people to really do this. He's a research scientist at Trout Nutrition, where he was eliciting these pre-weaning nutritional responses and following these animals for their entire life, which is a 10-year project, really. So kudos to this group to actually attempt to do that. That's extremely risky to do, and in my opinion, takes a lot of guts to do. So I think it's really cool that they're one of the first groups to actually follow these animals with really mechanistic measurements, looking at metabolomics and glucose tolerance tests throughout their entire life, in addition to their production responses. So unfortunately, I can't really answer that question, Morteza, of what this does long term, but based on the data we're gathering, I have a suspicion that it's actually impacting these calves long term when they reach the milk line. We just need to keep on following them.
Yeah, thank you.
But if we look at infant nutrition research, we have some indications that those high lactose and high protein milk replacers may affect metabolism long term.
Yeah. Great. We have a question from Hert Klassen, who actually plays the major role in formulating all of these diets. And we're the research scientists that say we want this, and then Hertz, through his experience, I believe like several decades, if not immense amount of experience, has helped us formulate all of these diets, which is really critical to the success of these particular studies. So, Hert, we're looking forward to your question.
Yeah, I saw some interesting stuff about the fluidity of the membranes. I know whole milk contains phospholipids, which are not so much in the milk replacer. What effect can we expect from the phospholipids in the whole milk?
Who wants to take that on first? Siobhan or Annemiek or Juliette, or, well, Juanita, you could take it on too. What do you think the phospholipids are doing?
Siobhan, go ahead.
Yes.
All right. Yeah, I'll take this away. That was my stuff. So I think there are some studies looking at specifically the phospholipids are found in the milk fat globule membrane. So there are some studies looking at supplementing milk fat globule membrane to rats, and it can alter the permeability. So I would expect that it would also alter the membrane fluidity, although we don't have a great concept of how they are incorporated into the membranes. I think a lot of it too would be the differences in the milk fat globule itself, and as I was referring to, the fatty acid profile, because it's quite reflective in those membranes. So yeah, I would say it definitely will affect the permeability. And there's a publication in rats in JDS right now. I believe the author is Snow, and they supplemented milk fat globule membranes, which is what's containing those phospholipids, and it changed permeability, but they didn't measure membrane fluidity, but they are related. So I would think it would be a similar effect.
Okay, thank you.
Yeah, thanks for your question. Any other comments on that question? Okay.
Any last, I'm cognizant of the time, any last questions for Mike or his group? Probably one more question if there's one out there. No? Okay. If not, then I would like to thank Mike and his group for an exceptional presentation and showmanship as well. Thanks for rounding out our year with a great presentation, guys. I'd also like to thank everybody for attending. I think we've had a really great year of CNM seminars, so just stay tuned for our 2022 lineup. And thanks again, everybody, and have a wonderful day.
Thank you.
Bye.
Thanks for coming, everyone.
Yes, bye.
Thank you so much.